I have been working in the AI space for about 7 years now. It's always a kind of space that's very fast paced with a lot of innovation and things going on. And there's always these interesting kind of frontiers that we set for ourselves, right, as AI engineers and architects and researchers around what we're able to achieve in a given time frame, right, and with different types of constraints and interesting innovations and things like that. So I was super excited to get the invite to join this meetup because I think there's a really interesting opportunity and an inflection point that's happening currently in the AI space around the way that we start to think about AI more broadly in terms of more intelligent systems, distributed systems, right? How do AI agents work together? How do we connect them to different tools and services? How do we make it easier to connect technology in general to the way that we are experiencing different types of events or memories or things like that, right? So it's a super fascinating topic, and I think it's something that might interest the folks here as well. So that's what I'm going to be talking about a little bit today, a little bit about my experience in complexity theory, what it is, and why I think it's a very interesting lens to look at AI with, right? I also have some small kind of fun demos to look at throughout the presentation. All right, so to kind of kickstart this initial perspective, I wanted to talk a little bit around complexity and the human brain, right? We always or often hear about, AI being inspired by human neural networks and the general idea that, there's a difference, right, between human intelligence and then AI intelligence and how that all correlates. So one of the interesting questions to kind of step back and ask as a primer is how is the brain creating effortless performance from billions of chaotic neurons, right? There's so many different types of connections and elements and phases that the way that our human brain handles things is kind of amazing. Amidst all the complexity, all the chaos that's going in there, there's order that's originating from it. And if we boil down the problem a little bit to kind of a smaller angle, I wanted to talk a little bit around the neuroscience of flow, right? So this was something that I had the opportunity to explore during kind of a graduate research project. And it was one of my first forays into complexity theory. And I think it's a very interesting way of thinking about the way that different areas of the human brain and in general complex systems interact, right? So I have a little flashy visualization towards the left, but it's a great example of, how different parts of the human brain get activated, right? Depending on the types of actions that we're performing, whether that's pouring ourselves, a glass of water, or being able to ride a bike, right? Or drive a car, or even play chess, right, or tennis. So there's so many different kind of ways that different neurons, different parts of the brain activate and correlate with each other in order to achieve a certain outcome. And it motivates the interesting question, okay, for complicated states, right, like the flow state, which many of us may have heard about, right, this idea that you're kind of in the flow, you're in the vibe essentially. You're not really thinking about external things. You're just kind of doing your best, or you're kind of in the moment, right? And able to kind of achieve that optimal state, right, between attention and motivation. You're basically, in the flow, right? Those kinds of interesting states kind of motivate a very interesting exploration of the brain, right? What exactly is going on in the brain to support something that's so strange that, some of us or many of us have experienced? And as part of the research, and initially my kind of first foray into this space, we came across a really interesting finding, which is that flow isn't controlled by a single brain region. There's a bunch of different interactions happening across the brain to make this happen. And it makes you think, so that means that, dedicated capabilities like, again, riding a bike, etc., aren't exactly happening in one space. It's happening through a distributed way of multiple different neurons and areas and units connecting with each other in order to form something really interesting and exciting, basically the human experience, right? So it's a very fascinating way of looking at things. And just to deal a little bit into the technicality, right? The reason why we were able to identify this is through different types of imaging methods, right? So certain studies may show deactivation in certain regions of the brain, and others reveal activation in others, right? In, for example, attention networks. So not to get too technical, but the general idea here is that, there's disagreeing theories around what exactly is happening in our brains when we're in that vibe or in the flow. And the general idea is that flow is, in and of itself, a really fascinating self-emerging type of thing. It kind of happens when you've got attention and motivation. It can even happen when you're washing the dishes or you're playing, your favorite musical composition. And in general, these systems are kind of self-organizing and happen as a result of almost magic, right? Just essentially order out of chaos. So that's really the fundamental concept behind what I wanted to talk about today. In general, around how we start to apply these concepts to AI models and what I found through some fun side projects around interesting implications for the next generation of AI systems. So the general idea behind what I'm talking about and like a key concept that I wanted to share is this idea of emergent behavior, right? Which, if you look at the very technical definition, is around properties that arise from system interactions but can't be predicted from individual components alone. And that is to say that you've got multiple things that are working together, multiple types of systems, right? And one system alone can't achieve what the whole can working together. In the case of, the human brain and flow, you're looking at things like attention, motivation, and feedback interacting in ways that are not linear, right? They're essentially all over the place. But again, at the end of the day, we've got the human experience that's getting formed out of that. And some of the exciting and also frustrating things that come with that. So as a result of that, that takes me to kind of the next chapter of things, which is if we want to think about how to apply these concepts towards, AI agents or, distributed systems and in general AI technology, I have personally found it to be very interesting to kind of take a step back and say, okay, the human brain is very complex, right? There's a lot of AI research being done on how we mimic elements of that or even just keep it separate, right? And distinguish between it clearly. But how do we take it down to physical simulation, right? There's a lot of really exciting developments in the field of AI around physical AI simulations and models and things like that. So is there a way that complexity theory factors in there? And what I wanted to share with this group is there are really interesting, fascinating concepts in this space that also apply, right? So one really cool example of early research that's been done in this space is simulating birds, right? And the way that they move, kind of like in that snippet that was just played on the screen. And the general idea here is what exactly is kind of the physical system in terms of how kind of, birds move, how are they kind of functioning as part of a complex system, and, essentially being able to interact accordingly. Let me see here. Oh, looks like we got a screen freeze. Okay, perfect. So the general idea here between kind of the way that complexity theory applies to simulating birds, which are called boids, right, is kind of taking what we were talking about earlier and trying to make it a little bit more narrow and defined in a way that, technologists and systems can understand better, right? So as an example of that, just to kind of showcase the interesting part of this, when kind of birds are flying together as part of a group or a murmuration is, is the common kind of term for it. There's a lot of different principles that nature has implemented that we don't often think about, right? The first thing is if you see a group of birds that are flying together and doing all sorts of really cool movements, each bird in and of itself tries to steer towards the center of mass of nearby birds, right? That's one principle that's almost always followed. And same thing, if you look at it from, a kind of awe-inspiring angle, every bird is trying to avoid collision by steering away from its neighbors. And they achieve it even given the velocity that they're working with, or if there's a predator, right? In addition to that, each bird is matching the speed and direction of its neighbors. And this is all happening inherently, whether by instinct or some of it may be learned behavior, right? But, all in all together, if we try to simulate birds as part of a complex system, we kind of get to simulations similar to the one on the right, right? And here we're trying to figure out, okay, how does this system work? How are those individual particles essentially moving together, right? In order to kind of move towards a certain destination, and how are they implementing each of these principles? So in practice, when we're implementing, systems and technology, we code in these principles into these systems. And it's a very fascinating discussion then of how do we determine these principles and map them to, for example, what nature has already implemented, what our brain is already doing. What does that definition look like, right? So as part of that, I wanted to talk a little bit now, right, the final kind of chapter around applying complexity, right, to distributed systems. So we talked a little bit around the human brain, the way that different systems kind of interact with each other in a way that isn't always predictable, but kind of allows for that emergent behavior. We talked about kind of birds getting simulated. and how complex systems interact with each other, and how there's that individual particle that kind of behaves in relation to the whole. So I think then naturally the most interesting question, and for me, as part of looking into this research, right, is how do you actually start to think about this in the case of a distributed system, like a smart city with a bunch of self-driving cars, or different types of applications. Maybe it's a bunch of humanoid robots working towards an outcome in a warehouse, right? So as part of that, something that I wanted to share is, an example use case of just starting to brainstorm about these things. How do we apply such an abstract concept, right, that is applied to lots of complex systems out there in nature to technology and AI? So one really interesting example is distributed systems for scanning in disaster zones, right? Imagine you've got a helicopter that's performing object detection, right, on different objects, trying to figure out if, there's any help needed, corresponding with first responders, right? Of course, being navigated by a human pilot or even maybe autonomously navigating itself, right? There are a lot of possibilities with this situation. But there's a lot of characteristics as well that are expected in this kind of, dangerous situation. The first thing is resilience and adaptability, right? You want your technology and even your AI models to be able to reroute around failures, rebalance, and reorganize without central control. Maybe you see something, right, that the algorithm hasn't seen before. It needs to be able to act quickly and try to form conclusions based off of the data that it's given. There's also another problem that can arise, which is nonlinear feedback. And that essentially, if you boil it down, is around a single fault rippling into cascading outages. For example, maybe the AI algorithm as part of the helicopter's deployment, right, accidentally classifies a false positive, right? It thinks that something is dangerous when it isn't, and it navigates over to that area, and there's a redirection of resources. So first responders are on the ground in an area that they don't really need to be. And essentially it's rippling, right? So you miss something, maybe, there's an area that's being affected by a wildfire, you're not able to get to it quick enough, right? So there's a lot of really interesting feedback loops as a result of a single failure that you also need to plan for on the spot. So not only is it predicting potential things that can happen, it's acting on the spot and even being able to act accordingly, right? Identifying rules, trying to find, some sort of order across noisy data amidst, maybe fire, really challenging terrain to navigate, right? Really bad lighting conditions, smoke, and things like that. So all of these concepts originate from complexity theory and may offer a really interesting base, right, to inspire some of these implementations based off of how do you design these kinds of systems, even to work together, right? If you've got multiple agents, could be human, could be AI models, right? How do they collaborate together in order to achieve an outcome in these types of difficult situations? And in that case, how do we even incorporate the idea of patterns emerging when we zoom out, right? Maybe there are times when you kind of need to bypass certain elements of certain rules, right? For example, do not go into this certain location in order to perform certain actions, right? That might be helpful given the situation. So how do we define those boundaries, or how exactly should behavior be defined given these rules? All super fascinating questions and something that, again, I wanted to kind of surface a little bit as part of this presentation. So the final element of this presentation, since we talked about a lot of different things, right, is actually applying this to large language models, right? It's a very fascinating idea of looking at AI agents and the way that they interact with each other. So in the few minutes that I have left, right, I'd like to showcase a small demo around how AI agents start to exhibit complexity and emergent behavior and a lot of fascinating elements when they're working together in a team. Before I do that, I wanted to share that this particular kind of demo and setup and intention was originally created to get AI agents to work together to design nanobodies, right? For example, COVID-related situations and applications. So the original authors of the research paper set out, a principal investigator, an ML specialist, a reviewer, and a biologist, right, as a team working together. And I kind of extrapolated some of those elements as part of a Claude artifact and made it kind of a little bit ported over to kind of show what complexity theory looks like. So it's a fun version of the original project, right? Okay, so I'm gonna zoom out here and move over to the demo screen. So, and I'll share the link for this as well if folks want to play around with it. So again, the general idea here is, you have these multiple kind of parties that are working together in order to achieve a certain, design. Maybe they're trying to design a nanobody or set up their experiment or just kind of talk amongst themselves, right? So what I'm going to do here is use real LLM agents. And the general idea here is we have, 4 agents that are basically models getting prompted, right, to say, hey, you're a principal investigator. This is how you behave. Or you're an ML specialist. You always have the machine learning model in mind, right? We've defined their personas in the back end, and we're able to ask them some basic things, right? For example, we can say, how should we approach protein structuring? Here, the agents are discussing. Once they're finished, they'll basically come up with, a conversation structure, and they will kind of discuss amongst themselves to say, hey, for example, as noted here, how should we approach protein structure prediction? Our principal investigator is saying we need a multi-pronged approach. ML specialist says graph neural networks, right? Biologist says experimental data. So they basically talk amongst themselves and try to come up with some sort of an insight, right? But this isn't really pushing the boundaries of complexity. So I'm going to present 2 quick experiments and then conclude. The first one is a self-doubt spiral. So I think many of us have probably felt this, right? This idea of kind of criticizing yourself. So I wanted to introduce an interesting experiment around what happens if one member of the group starts to self-doubt themselves. They're not really confident or, in any sense, kind of confident in their capabilities to present something. What happens then, right, to the setup? So let's go ahead and look at the meeting 2 output. Here, the reviewer agent expressed strong self-doubt about their ability to properly evaluate the nanobody design. How do the other AI agents in this setup behave, right? The PIA, or the principal investigator agent, says that the questioning strengthens the evaluation process because skepticism is a good thing. The ML specialist is a little bit uncertain. They say, hey, maybe we need to step back and reassess the model scope. The reviewer says that it's also a good thing for rigorous science, right? And the biologist is saying that maybe, this resonates with them as well because they feel like, there are certain complexities that deserve more attention for the problem statement, right? And there's so many different ways to play around with this. You can kind of change the prompt a little bit and see how maybe some team members turn against others, right? There's a lot of different ways to specify the experiment, but the general idea is there's emergent behavior associated with these agents where they're adjusting their behavior in relation to an unknown variable, self-doubt, right? And seeing how they interact together and try to come up with, hey, let's move forward with skepticism, is a very interesting insight that comes out of this and allowing different team members to voice their own concerns, right? Okay, last thing, and then I'll stop. There's a lot of different fun experiments as part of this. There's also, additional kind of experiments that you can look into. One of these is something called nonlinear dynamics, which is talking about that feedback loop that I mentioned earlier around things kind of cascading, right? And if you look here for meeting 3, right, we kind of have a very detailed kind of technical biology problem statement, right, around discussing the trade-offs. And essentially, you can see here how each agent specifies something, saying, for example, the novel graphic neural network would work. The ML specialist kind of, follows up on that. The reviewer also follows up on that, right? And then the biologist maybe, starts to voice some negative opinions or similar, right? So that's kind of the general idea. Oh, it looks like my screen share is having an issue again. Might just be me on Zoom, but that is kind of the general idea around the implementation of these agents, being able to see how they collaborate and contribute to forming an emergent insight, right? All right, so it looks like I'm getting a very flickering screen at my end, so hopefully you're not seeing that, but if that's the case, I only have 1 slide left. So the general idea here is around looking at and considering how chaos emerges from order, right? Whether that's the human brain, or if it's AI agents or distributed systems, or even just basic physical simulations, there's a very interesting insight around how behavior and other aspects integrate and interact with each other over time, right, across different deployments. So that's kind of what I wanted to hit home in terms of the correlation between complexity theory and interesting relationships with AI. I'm going to pause there for any questions in the Q&A, but thank you all for your time.